All right, the next topic we're going to explore is that of logistics. This is a better way to represent exponential growth in many situations where you have a limit. So, like mostly like population or sales, anything that involves kind of a real life scenario where you have this maximum amount that can exist or be sold. So this is known as the carrying capacity. So think about the world when we have population in an area. Uh, the land can really only support a certain amount. We can't just continue to grow exponentially with support to allow that population to exist. So a logistics model is a little bit different than exponential growth. It's based on the same premise though. Um, so when we looked at exponential growth, we started with a differential equation, and then we solved the differential to get this equation for exponential growth. We have the same thing with logistics. So we're starting off with this differential equation. And if we were to go ahead and solve the differential, which we can go through, I'll go through it in another video how to solve this. But we would end up with this equation, this exponential logistic growth model. So you'll see this written various ways. It's in the same format, but you'll see different variables associated with it. A lot of the times your carrying capacity is defined by M in most models. So the C value right now is known as the carrying capacity in this version. But sometimes you'll see an M as well. So we just have to know that if it's in this format, the top number is the carrying capacity. So that's the maximum number that can occur in the model. Sometimes you'll see a C here, which when we dealt with exponential growth, we knew the C was our initial value. That's not the case in this type. So logistics, we actually have to find the D value or the A value, whatever's there. And we know that we had to find a K when we dealt with exponential growth. We're doing the same thing. But this is a little bit different because we have this C value, this carrying capacity in that as well. So CK, a lot of the times, you'll see it as one number, and that's known as the growth rate. So it's either going to be an exponential decay problem or growth, or logistic growth and logistic decay. And we have to remember that this negative sign's out here. So we can either remember this model from the differential, or we can solve it. So let's get into a couple examples here. So it's pretty straightforward on how we do this, and it's very similar to what we did with exponential growth and exponential decay. So let's see, a high school has 1,300 students. The four honor society officers, Matt, Scott, Rena, and Lisa, along with 21 other members, spread a rumor on day 0 that Mr. Schwartz is to become principal. A day later, 62 students know the rumor. What happens over 10 days, and when is the rumor growing the fastest? So these are very typical things that are asked of you in a logistic problem and an exponential problem. So very similar. So carrying capacity. So how many students can know the rumor at most? Well, 1,300 students in the school, so that's going to be our carrying capacity. So that's going to be the C value here. So we'll keep that in mind here. And we can just write things out as we know them. So C value is 1,300. That's our carrying capacity. We have 4 Honor Society officers along with 21 members. So we know on day 0, so time, let's see, P of 0, 25 people knew. So the 21 members plus the 4 officers. It said a day later, 62 students know. So we know P of 1 is 62, sorry. And then they want us to know what P of 10 is. We don't know that. So we're going to put that. That's what we're finding. And then when is the rumor spreading the fastest? We'll talk about that at the very end. So just like any other problem that we dealt with exponentials, we plug in what we know to find what we don't know. So do we know anything about a growth rate? The answer is no. So we're not going to use the differential. We would have to know a growth rate to use the differential. So we're going to go ahead and use our logistic growth model. So we're going to plug in. We know P of 0. So let's start there. P of 0 is 25. Carrying capacity is 1,300. We have this 1 plus, we don't know this D. And then E to the negative. There's our carrying capacity, 1,300. The K we do not know. The time we know right now is 0 because that's what we're dealing with, P of 0. So it doesn't matter what K is because anything times 0 is just 0. So we get E to the 0, which is just 1. So this is what we have right now. We have 1,300 over 1 plus D equals 25. So we plugged in what we know and then find what we don't know. So D is what we're able to solve for right now. So the D value, we switch these two, we'll do this. I do 1,300 divided by 25 equals D plus 1. And then D would equal, let's see, 1,300 divided by 25 minus 1 is 51. So D is 51. So we have that information now. So now we can go ahead and start back at ground zero, okay? And then plug in P of 1. So P of 1 is 62. All right, and then we have 1,300 over 1 plus, now we know our D value now, so 51. E, -1, 3K times 1. That's the time we're dealing with right now, P of 1. So now we can solve for K. So if we go put everything over here, so that'll equal 1,300 over 62. Subtract 1, divide by 51. We end up with e to the negative 1,300k equals 1,300. I'm just going to leave them as fractions right now. Let's see, subtract 1. And then we're dividing all of that by 51. And let's continue on. We need to get rid of that e, so we're going to natural log both sides. And then divide by negative 1,300. So we get k equals... And obviously at the end we can get a decimal here, but so we're natural logging all of this, and we're dividing that whole amount by negative 1,300. So there's your k value. Okay, so we can leave it like this if we're going to use it in further cases, which we are when we're solving for P of 10. You can leave it like that, or make sure you use the answer key from your calculator. So I'm going to go ahead and get that put in so we can go and use that. So as long as we're close to our answer, we're going to be fine. Let's see. So go ahead and put that in and make sure we get the same thing. So our K value is, like I said, we can have that stored in there. So we have 0.000721. Okay, so that's good enough. We use 6 decimal places. That'll be good. So we have that as our K value. Okay. Now we can go ahead and find out what P of 10 is. So we have our D, we have our K, we know our C, so we know everything. So we'll be able to solve now. So let's do that. Let's find P of 10. P of 10 would equal, I'm just going to write this out for you so you have this in your notes. So 1300 over, so we still have that D of 51. So our negative C times our K, which is right here. So we can punch that in, remember, in here, or we can throw that answer out there. Either way is going to work out for us. And then we're multiplying by 10, because that's our time. Okay, so let's go ahead and crunch this. So we get an answer, P of 10 is, and I would type all that out if I were you. Make sure you're going to get the same answer as me, which was 1294.412. Okay, so we're going to answer that. So 1294.412. Now we could say 1294, we could say 1295. Does 0.4 of a person signify that they know the answer or the rumor? I don't know. So either one's going to be good. So we have that. Now we need to find, it says, when is the rumor spreading the fastest? So if we think hard about this, we've dealt with problems like this before. We need to maximize our equation to find out when we have the fastest growth rate. So we dealt with this before. So if we were to plug in our equation, okay, so plugging in our differential equation with our C and our D and our K put in, so essentially this thing right here with X here, or T, whatever you want to do. If we were to graph that, what that's going to look like is something like this. It's going to come up, it's going to be an exponential growth problem for a while, and then it's going to flip, and it's going to start tapering off towards this asymptote. So logistic growth models have two asymptotes. They have the bottom one here, and then they have this top one. All right. So this line right here, this Y value, is our carrying capacity. This would be 1300 in this case. Okay. This point right here, this middle point, this is called, so this inflection point would be right here. If we follow it across, this is going to be 1/2 of our C value. So 1/2 our carrying capacity. So in this case, 650. So it flips. It comes up, it's growing really, really fast, and then it starts losing steam. Still growing, but we're losing steam here. We're flipping. So this is what we're looking for. We need to maximize our equation. So if we graphed it, we graph the derivative of p, we'd be able to find the maximum of the equation. So if we were to graph the derivative, it would look something like this. We'd have this little curve here. And we're trying to find the point to where it has the maximum y value. This would be a growth, so the highest growth would be at a certain value. So we would plug this into our calculator, use n derivative to graph the derivative, and then we find the maximum value here, which in this case is x or t would equal 4.193. So go ahead and do that. Pause the video, graph the derivative of this function, and make sure you get this as the maximum. The other thing you could do is graph the second derivative of the function and find out where it's 0. So the x-intercept. You should get the same value. So I would try both those, see what you like doing better, and then go from there. So that's when we would have growing the fastest would be this time. Let's take a look at one more example here before we wrap this video up. All right, so I'm not content with that rumor. Alex, Randy, Brian, and Kim start the next rumor that Mr. Schwartz will be president of the school board all by themselves. Okay, it travels with the same transmission coefficient, k, so same k value, so we don't need to solve for that. What happens over 10 days? And when is it spreading the fastest? So we have a little less work on our hand because we already know what our k is. So let's go ahead and put this, put some information down. So we know p of 0 in this case is, so Alex, Randy, Brian, and Kim, so 4 people. So p of 0, 4 people know. Okay. Travels with the same transmission coefficient. So k is, what did we put down? I think it was 721. Let's see. I'll go back. Yep, 721. So that's a 2. Okay. And then we need to find p of 10. So we know p of 0 is 4, so we need to find that d value again, though. That's going to change. So p of 0 equals, so 1300 over 1 plus d, e to the negative 1300. Well, it doesn't matter. Our k, I'm just going to write k because we're multiplying by 0 anyways. So we know this e to the 0 is 1. So we have this situation again where it's 4 equals this 1300 over 1 plus d. Now we can go ahead and solve for d. Okay, so we have 1300 divided by 4 minus 1. So we have d is 324. And now we take this and we plug it into our equation. So we want to know p of 10. We already know k, so we don't have to do that step. So p of 10, sorry. That's terrible looking. I have to get rid of that. P of 10 0.00721 times 10. Multiply that out. Simplify. Let's see what we get. Go ahead and do that. $1265.162. Okay, so not too far off. Starting with a lot less people. We only started with 4 this time instead of 25, and we got pretty close to the same number. It's pretty cool. All right, so now what we would do is we would take, remember this equation, find first derivative, find the max, or second derivative, and find the 0. Remember that 10 is going to be an x when we're graphing. So it's growing the fastest at 6.165. So make sure you get that value. So time, that's the fastest growth, is at 6 days, 6.165 days. All right, so let me know if you have any questions on this. I mean, it's pretty straightforward. You're taking values that you know you're plugging in to find unknowns. The biggest part here is knowing your two equations, just like exponential growth. That's really all it boils down to. So there's really not a whole lot of calculus involved unless you want to remember this differential and then solve to find the growth model, the logistic growth model. Other words, there's really no calculus. It's all algebra. All right, so let me know if you have any questions and we can talk about this.